NASA is not slowing down on Mars. On February 24, 2026, at the Jet Propulsion Laboratory in Pasadena, engineers fired up a prototype magneto-plasma dynamic thruster, an electric engine running on lithium metal vapor, and hit 120 kilowatts of power, making it more than 25 times more powerful than the electric thrusters currently flying on any active NASA spacecraft. The comparison point is Psyche, NASA's asteroid mission currently operating the highest power electric propulsion system the agency has ever flown in space. This thruster makes Psyche's engines look like a flashlight next to a stadium floodlight. Electric propulsion is not new. NASA has been developing and flying electric thrusters since the 1960s, and the core principle is straightforward. Instead of burning chemical propellant to produce thrust, an electric thruster uses power to accelerate propellant electromagnetically, consuming up to 90% less fuel than a chemical rocket for the same change in velocity. The trade-off is thrust level. Electric thrusters produce a gentle, continuous push rather than the explosive force of a chemical engine. But in deep space, where there is no atmosphere and no urgency to the acceleration, that gentle, continuous push, applied over months, adds up to velocities no chemical rocket can match without carrying an impractical amount of propellant. For a crewed Mars mission, that efficiency is not a preference, it is a requirement. Mars is not a quick trip. At closest approach, when Earth and Mars align on the same side of the Sun every 26 months, the distance between the two planets narrows to around 54 million kilometers. At their furthest apart, it stretches past 400 million. The average transit distance for a crewed mission, calculated across realistic launch windows, sits at roughly 225 million kilometers, a journey that current chemical propulsion would take 7 to 9 months to cover one way, with the crew exposed to deep space radiation the entire time, in a vehicle that needs to carry enough propellant not just to get there, but to slow down on arrival and eventually launch back toward Earth. The surface they would arrive at is not hospitable. Average temperatures on Mars sit around -60 degrees Celsius, dropping to -125 at the poles in winter, with occasional highs near the equator in summer reaching a relatively mild -20. The atmosphere provides no thermal insulation worth calculating. A chemical propulsion architecture for a crewed Mars mission would require launching an enormous amount of propellant mass from Earth, mass that costs an extraordinary amount to lift out of Earth's gravity well and then has to be carried across 225 million kilometers before it is even used. Nuclear electric propulsion solves both problems simultaneously. The MPD thruster NASA tested in February requires a nuclear power source to operate at the multi-megawatt levels a crewed Mars mission would need, somewhere between 2 and 4 megawatts total, running continuously for over 23,000 hours across the mission. A nuclear reactor in space produces that power without solar panels the size of a football field, without degradation as the spacecraft moves further from the Sun and the available solar energy drops. The combination of nuclear power and electric propulsion does not just make a Mars mission faster, it makes the mass budget manageable enough that the mission becomes viable at all. Perseverance is already running on nuclear power. Right now, on the floor of Jezero crater, the rover is powered by a multi-mission radioisotope thermoelectric generator, an MMRTG, a device that converts the heat produced by the radioactive decay of plutonium-238 into electricity continuously, without solar panels, without batteries that need recharging, without any dependence on how much sunlight reaches the Martian surface on any given day. It produces around 110 watts of electrical power at the start of the mission, declining slowly over years as the plutonium decays. That is enough to run the rover's computers, instruments, wheels, robotic arm, drill, and heating systems simultaneously. The Curiosity rover uses the same system and has been operating for over 13 years on the same nuclear power source. Nuclear energy is the only power source currently available that provides continuous, reliable, high-density energy output regardless of distance from the sun, regardless of dust storms blocking solar panels, regardless of the mission duration. The next step is combining the two, a nuclear reactor in space driving multiple MPD thrusters across a 7-month transit to Mars, decelerating into Mars orbit and keeping the crew alive the entire way. Perseverance has been doing the advance work on the surface for 5 years. The propulsion system that will eventually carry humans to the same planet just had its first serious test 2 months ago.